Funding for this program is provided by Annenberg CPB to advance excellent teaching.
Somewhere between science and fantasy is a murky zone that's always been the most fertile ground for uninhibited new ideas. Eventually, these ideas fade into the mists of history like the music of the spheres, or they become ossified into mere superstition like alchemy and astrology. But first, they may haunt the human imagination for centuries, and they have their effect on science and on scientists. Today, I'd like to tell you about one of those shadowy ideas. Roger Boscovich was born in 1711, the son of an Italian mother and a Yugoslavian father. He was trained as a Jesuit, and he became many things. He was an architect, an archaeologist, a diplomat, an author, and more besides. He was not a scientist, but his was a more enlightened age than ours, and so he was well read in the sciences. And he had an idea. He said, look, suppose matter is made up of point masses of atoms. That's a very old idea. What's new about it, he said, is that we now know from Isaac Newton that when these masses are far apart, there's a force acting between them. And he drew a diagram. It looked like this. Here is force, here is zero, and on this axis, the distance between two atoms. Now, when the two atoms are far apart, he said, we know that the force between them is attractive, that is less than zero, below this line, and as they get closer together, it becomes bigger, further from zero. It goes as 1 over r squared. But, he said, we know that's true only when the two particles, the two atoms, are very far apart. We can't be sure that that remains true when they become very, very close together. Suppose when they become close together, the force turns around and becomes, instead of attractive, repulsive. That is to say, it goes up above zero on this kind of a diagram. It would look like that. Then when they're closer still, who knows, it might turn around and become attractive again, like that, and perhaps repulsive again, like that, and so on. Now, he said, if the force looks like this, then when the atoms are this far apart, there's no force between them at all. This is the point where the force is zero. And again, when they're this far apart, and again, when they're this far apart, there would be no force between the atoms at all. But these positions are not equivalent to each other. At this position, for example, although the force is zero here, if the two atoms move a little bit further apart, the force becomes positive or repulsive and tries to push them even further apart. And if the two atoms move a little bit closer together, the force becomes attractive, negative, and tries to pull them even closer together. And so, although there is no force at this position, the position is not stable. On the other hand, suppose they're in this position right here. Then there's no force between them, and if they should happen to move a little bit closer together, the force between them becomes positive, repulsive, and tries to push them back to where they were. And if they should try to move a little bit further apart, the force between them becomes attractive, negative, and tries to pull them back to where they were. And so that position is a position of stable equilibrium. So the idea is that atoms can be bound into stable webs of matter, making up the world that we can see. This is not a legitimate scientific idea because it makes no prediction. There's no way to test it to see if it's right. And yet it's an extraordinary idea. The idea is that matter is made up of atoms bound by fields of force into positions of stable equilibrium. The legitimate scientific discovery of atoms was made in the next century by John Dalton. And the legitimate scientific discovery of fields of force was made in the next century by Michael Faraday. But both of those men had been deeply impressed by this strange and shadowy idea of Roger Boscovich.
Stability, the state of an object that returns to its starting point when it's disturbed. Like a marble in a bowl, every atom in every piece of solid in the mechanical universe is in a position of stable equilibrium, not unlike the web of matter imagined by Roger Boscovich. But while Boscovich conceived of stability in terms of the play of Newtonian forces, the idea is better grasped in the dynamic concept of energy. Perhaps nobody appreciates the flow of energy more than a firefighter, particularly when the heat's on. Heat is energy. And energy, in its many forms, is one of the more dynamic properties of the universe. Whatever its form, no matter its purpose, energy is everywhere. It always will be, and it always was. No matter how it's used or abused, the total amount of energy in the universe never decreases. In the storehouse of the cosmos, the shelves are as amply stocked today as they were the morning the universe opened for business. That's because energy is conserved, without exception, strictly and absolutely. Energy cannot be created, nor can it be destroyed. But it can be changed into different forms. Energy can be potential, and energy can be kinetic.
3, 2, 1, ignition.
Energy can be almost heavenly, and it can cause sheer hell. But no matter where or how, even when the heat's off, energy flows from one thing to another, even from a sandwich to a student firefighter. Energy flows in many ways, in many forms, and to and from many things. And energy is stored in many ways, forms, and things. It's stored in the form of potential energy. For instance, stored in a tank of gasoline, which is loaded with potential energy waiting to be converted. And wherever it's stored, potential energy depends on position. Not the position of the tank, but in this example, in the positions of the atoms within the molecules of the gasoline. The way any object stores potential energy depends on the object's position. The higher above the Earth any object is, the more gravitational potential energy it has. And the potential energy changes with the object's position. The closer an object gets to the ground, the less potential energy it has. Obviously, then, potential energy is related to position. While potential energy relates to position, kinetic energy is related to speed. Clearly, a fast-moving body has more kinetic energy than a slow-moving one. However, anybody can trade potential energy for kinetic energy by trading position for speed. In much the same way that an object's potential energy depends on its position near the Earth, an atom's potential energy depends on its position within the matter it's bound to. The molecules within the oil have plenty of potential energy. Their atoms are bound together into molecules by the electrical force between atoms. When ignited, they become rearranged into other molecules that contain less potential energy. Young firefighters who learn to respect this phenomenon have the potential to become old firefighters. Regardless of specific age and circumstance, the firefighter's essential responsibility is to put out the fire. That job often requires water. First getting the water, and then getting the water from ground level to the flame. Water! To do that means, in effect, to endow the water with potential energy. Once again, the ubiquitous flow of energy can be seen, even in the flow of water. There's work to be done here, and that work, provided by the force of the water pressure, at first turns into the kinetic energy of the water leaving the nozzle at high speed. Now, as the water rises against the force of gravity, some of the kinetic energy turns into potential energy. With a good crew and enough pressure behind it, the water can soar to its destination. One way or another, humans have always wanted to soar higher and higher. In this century, several rose as high as 400,000 kilometers. And in the last century, the pull upward was just as strong, at least in the far-reaching imagination of Jules Verne. The lunar journey he imagined was taken on the wings of a cannonball rocket. Far-fetched? Perhaps. But according to Jules Verne, to reach the moon, all space travelers needed was enough kinetic energy to begin with. Beyond the realm of science fiction, the moon's gravity can indeed help a projectile finish its journey. As far as it goes, that much is true. But could a vessel really escape from the Earth without an engine of its own? The idea has a lot of potential, but getting there will take some work. The work required to lift an object away from the surface of the Earth is given by the force of gravity integrated over the distance. The work is the change in potential energy. If the vessel is lifted to infinity, it has a potential energy of 0. This means that back on the surface of the Earth, its potential energy is negative. To escape from the Earth, it must be given some kinetic energy, enough so that it will not slow down to zero before it gets infinitely far away. The total energy is zero, both at infinity and on the surface. The vessel will escape if it starts with a speed of about 11 kilometers per second. While astronauts zoom upward with rockets, firefighters tend to head toward their destination upward under their own power. Safety precautions usually close the door on the elevator. And when a forklift isn't handy, that leaves the feet. Firefighters need more than sure footing to climb ladders. They need energy. What's the source of all that energy? The food they eat. To anyone who needs a certain amount of energy to get the job done, the fact that human energy comes from food may be no surprise at all. This fact, however, may come as a surprise. The amount of food it takes to get the job done can be calculated. Consider, for example, this firefighter's task and the factors involved. The potential energy needed has to equal mg h. That's his mass, times the acceleration of gravity, times the height he reaches. An average firefighter wearing gear weighs 90 kilograms. The acceleration of gravity is about 10 meters per second squared. A 10-story building is about 30 meters high. Therefore, the firefighter's final potential energy, if he were to go as high as 10 floors up, will be 90 times 10 times 30, or 27,000 kilogram meters squared per second squared, also known as joules, and named after James Prescott Joule. Joule demonstrated that about 4.2 joules are equivalent to 1 calorie of heat. So, the firefighter's potential energy, mgh, amounts to a little over 6,000 calories. But a food calorie, the kind diet books go on and on about with a capital C, is actually 1,000 heat calories. So, the net result of all this firefighter's efforts, if he were to climb to the top of a 10-story building, would be to turn about 6 food calories from his energy reserves into potential energy. That's the tiny fraction transferred to the potential energy of his body, 30 meters above the ground. For turning food energy into mechanical energy, the human body is an amazingly inefficient machine. Mostly, that machine uses energy just to keep itself going, breathing, digesting, metabolizing, and merely staying alive. But sometimes, that tiny fraction seems to count for everything. That tiny bit becomes muscular force times height. That crumb of food energy turns into work, and work itself is the transfer of energy from one form to another. For example, a sprinter works against his own inertia and turns food energy into kinetic energy. A pole vaulter also starts by doing the work to get himself moving. But in terms of energy, he takes things farther. Now that he has kinetic energy, the vaulter can turn it into potential energy, which is stored in the pole. That, in turn, becomes the potential energy of his own body soaring over the bar. At this point, his potential energy turns back into kinetic energy, which is finally dissipated into useless heat. Just to keep the body alive, humans constantly turn food energy into other forms of energy. And even when an athlete works her body to the utmost, she turns only a fraction of her food energy into the kinetic or potential variety. Yet no matter the amount used, bodies in motion illustrate the idea of energy. And no matter the activity, propelling the body is work. Work is a force, in this case a muscular force, applied through a distance. Work shifts energy from one system to another. For example, from the interior of that infinitely complex machine, the human body, to a far more simple and visible form, such as the kinetic and potential energy of a discus in flight, or the potential energy of someone climbing a ladder. Of course, climbing a ladder requires balance. And so does washing windows. In the physical realm, when all the forces are balanced, equilibrium exists. But mere equilibrium doesn't ensure safety. Safety, no chance rolling, sliding, stumbling, or otherwise coming to harm, requires a special kind of equilibrium. It's called stable equilibrium.
Stable equilibrium can always be seen on a graph of potential energy versus position. The force on a body tends to push it toward positions of lower potential energy. The steeper the slope, the bigger the force that results. In fact, the force is just equal to minus the rate of change of potential energy. Since it depends on the slope of the potential energy, not its size, potential energy can be positive or negative without changing its effect. Of course, when the slope is zero, there is no force on the body. It is in equilibrium.
That equilibrium may be stable, like being securely nestled in a valley. Or it can be unstable, like being precariously perched on a peak. Seen in terms of force, this is exactly the picture Roger Boscovich had in mind. For example, the potential energy of a pair of hydrogen atoms has a position of stable equilibrium. The potential energies of interactions between atoms are due to the electrical forces between them, causing attraction when they're far apart. At smaller distances, they resist being squeezed together. The result is an equilibrium position where attraction and repulsion are in perfect balance. At that position, they bind into a hydrogen molecule. Balanced on the rungs of the firefighter's ladder, potential energy depends on position. Potential energy is reduced by moving to a location nearer the ground. The place where potential energy is lowest, where something can fall no farther, is the only place where stability no longer matters. When an object starts from and returns to the same elevation, there's a net potential energy change of zero. Therefore, from a physics point of view, despite all this healthy activity, no net work has been accomplished. At the same time, because of all this healthy activity, it looks as if a lot of work gets done. The curious part, from an historical perspective, is that these bodies volunteer to do it. Back in the bad old days, machines were likewise used to transmit and amplify forces, but the subjects were hardly voluntary. Unlike the machines of today, which extend the body's endurance, these machines extended the body itself. Often the mere sight of such machines would influence the wrongdoer to confess all manner of transgressions, real or imagined. This practice, which was used very effectively on countless terrified prisoners, was called showing the instruments.
We've now reached a critical juncture in the evolution of this course. We've learned about force and acceleration, energy, work, in fact, all of the tools that you need to solve problems in mechanics. What kind of problems are you prepared to solve? Here's a good example. Here's an inclined plane. On the plane there's a cart. The cart has some mass. Here's the cart. The mass applies a force straight down. There's a string attached to it, which runs up over a pulley and comes down, and there's another mass hanging from that, applying a force down this direction, like that. There's some coefficient of friction at this point here between the cart and the plane. The plane is inclined at some definite angle, theta. And then the question might be, for example, how big does this mass have to be in order to make the cart just barely start moving like that? And you know everything you need to know in order to be able to solve that problem. Now you might reasonably ask, in what way will world culture be advanced if you manage to find a solution to that problem? And the answer is that it won't be, of course. But it would give you a chance to try out the tools that you've learned, and it will give me some peace and quiet while you're busy trying to solve the problem. And above all, it's traditional. 100 generations of students of mechanics have had to grind their way through problems on inclined planes and pulleys. We know from letters written in the 17th century that even then students considered mechanics to be a dull subject. And so we have a crisis. Our job is to get you excited about learning science, and we've reached the point where it's traditional to grind you down with endless problems about pulleys and inclined planes. And what do we do about it? Well, the committees that govern what we do in this course have met to debate and deliberate on that problem. And they finally come to a decision, and they've given me the decision. They've authorized me to show you the instruments. I'll see you next time.